What's the strangest, most bizarre, most impossible thing in the universe that breaks every known law of physics? Black holes. But do they really exist? The shocking truth is, Earth is already heading toward one. So what happens next? What will be the fate of our planet? And most importantly, what's going to happen to us? It truly stands at the center of some of the biggest and most heated debates in the world of physics and science as a whole. Let's go back to Newton's time. After he proposed the law of universal gravitation, naturally, everyone started talking about it. Different scientists who interpreted this law were all arriving at the same conclusion at some point. As an object's mass increases, naturally, its gravitational pull should also become stronger. So in that case, anything trying to escape from such a massive object would have to move much faster. So, what if an object had a mass so immense it pushed the limits of our imagination, like dozens of times more massive than our sun? Naturally, even light wouldn't be able to escape it. And that's exactly how our very first assumption about black holes was formed, around 400 years ago. A dark star, not such a wrong conclusion. In fact, for that time, it was a pretty accurate one. They just had no idea what would truly happen if an object that massive actually existed. Because no matter what, the idea of something that even light couldn't escape from just didn't seem acceptable. For a long time, many scientists in the field of physics, even the biggest names, believed such a thing simply wasn't possible. But the real debates began about 100 years ago, with another revolution in the world of physics. And of course, with the man behind that revolution, Albert Einstein. As you know, with the theory of general relativity, Einstein changed everything. We talked a lot about this in our video, What is Time? Many mysteries are revealed there. I'm placing a card for that video here. Be sure to check it out later. As we create these videos, we're diving into some very deep topics. Our goal is to combine science and speculation to present useful information. You can support us by sharing your thoughts, new research topics, and requests in the comments. In previous videos, we talked about time and how the universe is like a fabric, where the bigger an object is, the more it bends that fabric. Time bends too, and at a certain point, it can come to a halt, stopping time. Building on this revolutionary theory, German physicist Karl Schwarzschild made a wild deduction. If you keep an object's mass constant and shrink its size as much as atoms allow, its density will increase incredibly, and the curvature of space-time will increase proportionally. For example, if we take our sun, it could be shrunk down to just 3 kilometers in diameter. Or if we shrink Earth to just 9 millimeters, which would fit into the size of a standard bullet. This is something that could theoretically happen. So, this isn't just any simple bending. The density would reach such a level at a certain point that space-time could bend infinitely. Infinity. The thing is, infinity is a conclusion we've drawn because of our limitations. If Earth were to shrink to just 9 millimeters, the object would bend space-time so much that light wouldn't even be able to escape it, and we wouldn't be able to see it. This threshold of density, where light can't escape, is called the event horizon. It's the starting point for the concept of black holes. Yet, despite all these assumptions and the support from theories, no one believed that such a thing actually existed in the universe. This was something that completely shattered the laws of physics. However, there was a lesser-known name. A 19-year-old Indian young genius, Chandrasekhar, had something to say on this matter. Thanks to his work on the internal structure of stars, he was accepted into Cambridge University, and in the 1930s, his research on white dwarfs would spark a breakthrough. A white dwarf is an object that forms after the death of a star that has exhausted its nuclear fuel. However, there is a limit to how much these stars can shrink. They eject part of their mass in a type of explosion, and the remaining matter compresses into a small stellar remnant with increased density. There's a reason for this limit. Atoms allow a material to shrink only to a certain point. So, a white dwarf could be the size of Earth, but with the mass of the sun. Think of it like a sugar cube weighing several tons. That's the kind of density we're talking about. While Chandrasekhar was conducting his research in England, everyone believed that at the end of every star's life, it would turn into a white dwarf and complete its life cycle this way. He believed there was a limit to how much atoms could compress. However, Chandrasekhar's calculations told a very different story. They suggested that, after exceeding a certain mass limit, these white dwarfs would continue to collapse and shrink toward infinity. Previously, it was believed that the maximum limit for how much a star could shrink was around a 10,000 kilometer diameter. But Chandrasekhar discovered that if a star had a mass about 1.4 times that of our sun, it wouldn't be able to withstand its own gravitational pull and would continue to collapse toward infinity. This is the simplest definition of a black hole. However, of course, these findings were met with significant resistance in the scientific community. At that time, there was another name in Cambridge where Chandrasekhar was, Sir Arthur Eddington. He was going to strongly oppose this finding. You might remember Eddington, right? He was one of Einstein's supporters, and the person who confirmed general relativity through a solar eclipse. But this idea seemed even too crazy for him. Let's say a star shrank down to a few kilometers. There's no problem with that, but anything beyond that, shrinking towards infinity as you said, would be considered absurd in its simplest form by Chandrasekhar. Despite this resistance, he would continue his work in the United States, and during this period, a new and very crazy discovery in the scientific world would further strengthen his claim. It was known that the atomic nucleus consists of protons and neutrons, with electrons orbiting around it. However, in 1932, it was discovered that under extreme compression, electrons and protons could merge to form a structure consisting solely of neutrons. It would be theoretically proven that this neutron could be compressed even further, and in a star about 1.4 times the size of our Sun, it could undergo a massive explosion and transform into one of the craziest structures in the universe, a neutron star. Like the neutron star in the Crab Nebula. The star surrounded by this nebula is a neutron star. We mentioned earlier that in a white dwarf, a sugar cube could weigh a few tons, but in a neutron star, imagine that a sugar cube could weigh hundreds of millions of tons. It's something so dense. We now knew that when a star dies, it might not leave behind a white dwarf. There was something beyond that, neutron stars. However, there would be resistance here as well, and everyone would say that the final point a star can reach is a neutron star, and that, beyond that, is impossible. Here, however, the voice of a completely different scientist would rise. One of the smartest, most controversial, most loved, or most hated scientists in history, Robert Oppenheimer. Oppenheimer, the Manhattan Project, atomic bombs, and much more. We'll talk about that a lot, but for now, let's not get off topic. Oppenheimer would make his own calculations and determine that if a star is 3 times the size of our Sun, it wouldn't remain as a neutron star when it dies, but would collapse into a black hole. But of course, the debates wouldn't end there. Another famous figure, John Wheeler, would oppose Oppenheimer and argue that when a star loses mass and shrinks down to the size of our Sun, collapse would begin. And in the end, it would either become a neutron star or a white dwarf. Anything beyond that, he said, was meaningless. No one could accept that such a strange thing could exist. Of course, just like all scientists should, he continued to work on it. He wanted to explain why it couldn't happen. The strange part is that it was John Wheeler himself who coined the term black hole in the scientific literature. However, as Wheeler delved deeper into this work, he became increasingly lost in it. He built all of his theories using general relativity, gravitational pull, and the concepts of space-time. On his quest to prove the impossibility of black holes, all the calculations pointed to just one thing. A black hole exists. In fact, it had to exist. There was no other explanation. The dream of a 19-year-old young man from India had come true, and even though many years had passed, his efforts would eventually be recognized, and in 1983, he would receive the Nobel Prize in Physics. So, finally, the existence of black holes was a reality. Furthermore, we even knew how they formed. We had a complete description, but something was missing. A black hole, meaning evidence. We didn't have any images or anything that could prove its existence. Now, a new adventure lay ahead. A challenge, finding the first black hole. It had become the dream of all scientists, to find something that was once considered impossible and prove it. Black holes. We had said at the beginning that they were one of the strangest phenomena in the universe, but beyond just being this strange monster we didn't know much about, they would open many other doors for us. It would offer answers to many questions we couldn't answer. Are black holes really black? Are black holes really holes? Moreover, you know the most important question in science, right? The greatest mystery. The question everyone is currently seeking the answer to. The gap between quantum physics and general relativity. The theory that will connect these two revolutionary phenomena. The theory of everything. Black holes might provide us with the answer to this as well. In fact, they have already offered us some answers, thanks to someone we've hardly ever mentioned until now. Someone as big as Newton and Einstein, Stephen Hawking. After a long journey, it's time to talk about him and his incredible genius. We'll be discussing him in several videos, and the number is hard to predict. But for now, let's first find the first black hole together in the next video. Let's not waste any more time. I'm counting on your support to ensure that these videos can continue for a long time, allowing more people to talk about science, and for science to thrive for many years. All the videos I've prepared and will prepare will be publicly available to everyone, but your support is crucial. Until we meet again, I'm so glad you're here.